they're part of the nucleus of the atom. If it's a solid, the atom doesn't move around. It may vibrate, but it doesn't move from one place to another place. But the electrons might have electrons that are free to move around, like a piece of copper. Every atom in a piece of copper metal, one of the electrons isn't tied down to that atom. That outermost electron isn't really tied down. It's free to move, therefore if it feels an electric force, it can move through the piece of metal. But the rest of them tend to be tied onto that one atom. Still neutrally charged. You have as many protons as you do electrons. But the electrons would redistribute themselves so that then the excess protons would be redistributed equally around the surface of the sphere. E would equal 0. So if you get into doing this mathematically three-dimensionally, again, all the electric fields would add up to 0 at the center, but not only at the center, anywhere inside here. The total electric field is going to be 0. If it's a conductor. This is, again, what's called static electricity. It's a conducting material. Any excess charge, either positive or negative, always ends up on the outer surface of the material. And the electric field inside that material then is going to be E equals 0. We didn't do it in my class anyway, but Newton was able to show using calculus that if you had a perfectly spherical mass, and really now you'd want it to be, since you're going to get down inside it, not solid, but if you had like a spherical shell, and on the inside of it is right at the center, the gravitational acceleration would be 0. Or if you could drill a hole through the earth, right through the center of the earth, and the earth was a perfect sphere, and it was uniform density throughout, then right at the center of the earth, you'd have gravitational acceleration equal to 0 at that point. Because all the other masses are trying to pull you in other directions, and they cancel each other out. Well, using calculus again, then you can show that for a spherical shell of charges, all those charges equally distributed around the outside surface, that right anywhere inside there, the electric field is going to equal 0. And then in chapter 22, we're skipping a little bit here, chapter 22, it turns out that you can show, using what's called Gauss's law, that it doesn't even have to be a perfect sphere. It can be any shape, as long as it's a conducting material and you're dealing with static electricity, as opposed to current electricity. You got current going through a wire. Now, it's not on the outside surface of the copper wire. It goes through the inner part of the wire. But if it's not moving charges, so it's a static charge as opposed to a moving current type charge, then no matter what the shape of the thing is, all of the excess charge would be on the outer surface. All these pluses here. So all of that, and on the inside, the electric field will be 0. Well, you should have negatives on the outside too. Which is basically the idea behind the lightning rod again. Lightning hits the piece of metal, it actually travels down the outer surface that electricity does of the metal. Now, there's so much that it really doesn't matter at that point, but when it's on the outside, and plus it's not a really thick, rod of metal. But all on the inside, it will equal 0, which is why, if you get caught in a lightning storm, where are the 2 safest places to be in a lightning storm besides somewhere else? One would be inside a building. In general, inside a building is going to be okay. The other would be in like a car or any automotive type of vehicle. At least the older ones. Now, some of the newer ones, if you get too much plastic, I'm not sure at that point. That's not being quite as safe anymore. But the older cars especially have a lot of metal. And if you're inside the car, unless you just have a direct hit by the lightning bolt on the car itself, may break windows and stuff like that, and then you might get injured from that. But from the electricity, that electricity from the lightning bolt, the charges are moving, but it's still the same as static electricity. It will go on the outside surface of the car because you're inside of that metal cage of the car, and therefore you are in a place where the electric field is 0. And if the electric field is 0, you can't have moving charges in there then. So if you had like an excess negative charge, an electron sitting there, well, then it's going to be attracted to all these others, and it will tend to move out to the end, and then that redistributes all the positive around the outer surface, and you go back to being no net charge on the inside, and therefore you've got electric field equals 0 at that point. So you're safe inside the car effectively. I've seen pictures, and actually I saw this demo live. Went to a conference up at Texas Tech about 15 years ago, and they were doing this. They had this cage, and the cage was probably this high and that wide at least, so about 2 meters wide and high. You could easily see inside the cage. Probably the bars or the wire more than anything going around it had openings that were about like that all the way around. 2-dimensional type of cage there. And so this student, probably a graduate student, gets inside the cage, sits down on a wooden chair inside the cage. Then they had a Van de Graaff generator, and it was a big one. We've got a small one upstairs, and if it's working, we can play with it sometime. Get some of your hair to stand up. But they had this big Van de Graaff generator, so they fire it up, and what it does, it creates electricity. And if the voltage difference between it and the ground or something else is big enough, then the force on the electrons that are being created can cause them to jump, say like from the big metal ball that's on top of the generator to the ground. Then upstairs, if you get too close to it when it's running, you'll have a spark jump from it to your arm. And it'll give you a pretty good shock. But they had this great big one going, and it's sending out these sparks that are like 6 feet long, from the generator, and it's hitting this cage, and the guy's inside the cage, and he's fine. He's not feeling any sort of a shock because he's inside this metal cage. The famous picture, there was a electrician for General Electric back in the early 1900s called Charles Steinmetz, I believe was his name. He invented a lot of the apparatuses that General Electric used to create electrical systems. And he was a showman. But he's sitting inside of one of these cages, and you got 4 of these great big generators around the room there, like in the corners, and it's effectively looks like lightning bolts. They're really big generators, and they're coming from the 4 corners, hitting his cage, and he's sitting inside there, you know, happy as a lark, smoking a cigar, and perfectly safe. So, yeah, if you're inside the metal container, and this is static electricity, okay, you're okay at that point. It won't bother you. Or if you're in a wreck and the live electric wire is draped across the hood of the car. So the car is electrified at that point. If the car isn't catching on fire or anything like that, then stay inside the car. Don't try to get out. The problem is if you try to get out, you're probably going to be touching the ground, say with your feet, and the car, either with your body or maybe your hand as you push your way out simultaneously. And that gives another way for that electricity to get from the car to the ground. And if it goes over the body, if it's large enough, in fact, if it's electric wire, it's going to be current electricity as opposed to static. And therefore, it will tend to go through the body. And you don't want electricity to go through the body. That's bad for you. Over the outside, that can give you bad shocks. That's why you don't go, stick the knife in the electrical outlet. That's current electricity. Electricity gets through the knife into your arm. It's going to go up the arm, through the torso of the body, down the leg, to the ground. And as it goes through the torso, it disrupts the electrical signal going to the heart from all the nerves. And if that gets disrupted, then your heart muscles don't know when to beat correctly. They get out of sync with each other. And your heart goes into fibrillation at that point. So it's fluttering instead of beating the way it's supposed to be. So how do you get it out of that fluttering state? You want to make it not fibrillate? What do you use? A defibrillator. What does a defibrillator do? It shocks you again. It hits you with another bolt of electricity there and tries to knock it back into that regular rhythm. And they hope it works. Or, how can you do that mechanically? How can you get the heart to beat in the regular rhythm mechanically as opposed to electrically, which is the defibrillator? CPR. You're just mechanically trying to make it beat correctly. And, if you get lucky, the person gets lucky, then it gets to doing that on its own after you've compress the heart, making it do it mechanically, and then they're okay. Or the defibrillator happens to shock them back into that regular rhythm. And if you're not, or if they're not, then they may or may not survive at that point. Anyway, all that good stuff about electricity. But inside of a conducting material, if it's static electricity, the electric field will be zero. What's called Gauss's law, and I'm just going to show you this. I will not test you on this. Gauss's law is the electric flux, written this way, capital PHI. If you think of these electric field lines, so like if you got the, say, a positive charge, electric field lines are going out in all directions, three-dimensionally, away from it. Or if it was a negative charge, then they're all coming in towards that charge. Or if you had a positive and a negative, It's going from the positive toward the negative. That'd be the net electric field there. But then over here, it starts doing things like, you see the field lines acting like that as they go around. The flux is a measurement of the amount of field lines going through an area. How dense are the field lines going through that area? That's the flux. Well, Gauss's law says the electric flux through a closed surface. You've got this charge, you surround it with a sphere, is the integral around the closed surface E dot dA, and that's basically writing. Technically, it's a dot product, like an EDA, cosine theta, between the E and the dA. But that will be the charge inside the surface divided by constant, which is epsilon naught. The epsilon naught constant, or put it this way, the K, this number, is 1 over 4 pi epsilon naught. The epsilon naught is called the permittivity of free space vacuum, but that's just a name. But we'll just do everything in terms of the K. There's one equation in a later chapter that has the epsilon naught in it by itself. But that's the relationship between the K and the epsilon naught. Well, epsilon naught works out as like 8.85 10 to the negative 12 as far as the number. Says it's the charge divided by the epsilon naught. But this doesn't even have to be a nice surface. It can be any surface. And so one example of calculating the electric field using Gauss's law as opposed to an integral of the K dq over R squared would be if you've got a line of charge and so this is an infinite line of charge. Straight line charge goes forever. You have a certain amount of charge per unit length. And so the charge per unit length, lambda, so that's Q over L, the way they'll write it. Well, what would be the electric field at some distance R away from this charge? Well, that would be, the integral isn't really that bad to do that because it's infinite, but it's still easier using Gauss's law. If I take a cylinder and put this line of charge right down the center of the cylinder, here's a cylindrical surface going around the line of charge. Well, this is right down the center, then all of this external, or this what's called the lateral surface of the cylinder is the same distance away from that line of charge. And so if I take by each little dq here, there's some distance there. Well, that would be an electric field pointing, say, in that direction. But since it's infinite, there must be another little dq over here that has an electric field going this way. The x components would cancel, and then you just have y components going up. So the net electric field around this lateral surface should be perpendicular to the surface. Got that? And since it's all the same distance from that surface, all the surface is the same distance at every point away from the line of charge, then the electric field should be constant around that lateral surface of your cylinder, at the sides of the Coke can. The dA, vectorially, an area vector is always perpendicular to the surface itself. So around this lateral surface, the dA is also perpendicular to the surface, and the E and the dA are parallel to each other, angle of 0. Dot product has the cosine, and therefore the cosine of 0 is 1. So it's just the integral of EDA, not getting into the dot product part. Okay, so that's going to be a constant E around this surface. Well, how about these two ends? Well, again, E is going to be going away from the line of charge, okay, but the dA here is going to be perpendicular to the surface, and so on the two ends, dA pointing that way and the E pointing that way, they're 90 degrees to each other, and the cosine of 90 is 0 on that dot product. And so the flux through these areas is going to be 0 flux. So the only net flux you have is through this lateral surface. And so I could say the integral of the E dot dA is going to be the E, since that's going to be constant, times the integral of that dA. Well, but that's just the area of that lateral surface area of the cylinder, and that would be given by 2 pi times the radius times the length of the cylinder. Well, but that's going to equal, according to Gauss's law, the charge inside the cylinder divided by the epsilon naught. Well, that says the E is the charge inside divided by 2 pi L R epsilon naught. But this charge inside of the cylinder divided by the length is that charge per unit length number for the infinite line of charge. So I can rewrite that as the charge per unit length over 2 pi epsilon naught R, which says that this electric field decreases as 1 over R as you move away from the infinite line of charge. Whereas with the point charge, electric field decreased as 1 over R squared. So what is it for an infinite line of charge? It's proportional to 1 over R. For a point charge, it's proportional to 1 over R squared. And that's using Gauss's law as opposed to the integral of the K dq over R squared to come up with that equation. You come up with the same equation if you did that integration. You have to think more in terms of the integration at that point. In this one, I didn't have to do that, because then I'm just basically doing, since the E was constant over that surface, all I had to look at was what's the area of the surface. Gauss's law works really well if you can get things like spherical symmetry for the problem, or if you could get a cylindrical type of symmetry involved. The other one is if it's an infinite plane of charge, like this, and you put a cylinder, actually the cylinder, like here's the plane, but you put the cylinder this way. Now this is all that. So again, the electric field pointing this way, but then the dA on the ends is now parallel to the electric field. The dA on the sides is now perpendicular. So you're only looking at the dA, these two parts, and you end up in of that the surface area charge distribution, and I think it's just divided by 2 epsilon naught, I believe, is the answer there. But essentially, it ends up being, it's constant. If that's an infinite plane of charge, whether I'm this far from the plane, or whether I'm that far from the plane, I've got the same electric field. It's a constant electric field no matter what the distance is, if it's infinite. Now, if it's not infinite, I've got the tabletop, it would be relatively constant if I'm right in the center of the table. So, pretty big distance away from the sides, and I don't get too far away from that tabletop. If I stay really close, it'll remain relatively constant for a certain distance there, and eventually it's going to start varying as it goes out, because it's not an infinite plane. That will come into play when we get into capacitors. A capacitor, and by the way, I think anyway, that's all we're going to do with Gauss's law. I'm just going to show you those examples. So if you happen to run into that in a later course, you take by going into electrical engineering, and you may run into some of that later. But I'm not going to test you on Gauss's law. Okay. But a capacitor, it's like, or at least the standard way of looking at it, you take two plates, make them parallel with each other. It's called a parallel plate capacitor. You got two plates, they have a certain area, and generally we think of it as being the same area. They don't have to be, but we think of generally the same area. They're separated here by some distance. And then if you put a charge on the two plates, so you've got some charge on these plates, then that charge creates an electric field in between the plates. And again, if you're not too close to the edge of the two plates, the electric field will be relatively constant electric field. So if these two plates close together and you're not out here right near the edge, you're going to have a constant electric field in between those two plates. Out here at the edge, it starts doing curving and stuff like that. So a variable electric field. But down in the center, you've got a constant electric field. So that's what we have with what's called a capacitor. If you take this capacitance and you hook it up to a battery, so here's our capacitor. We're going to call it capacitor C. And it's just going to be two straight lines, same length when I draw it in the circuit diagram. And now we're going to hook this up to a battery. And so here's our battery, which is a certain voltage, minus and plus. One long line, one short line. When you hook it up to the battery, there's an electric field externally to the battery itself that goes from the positive around to the negative. So you've got this electric field going around like this, outside the battery, not inside of it, but outside. Well, that means there's a force on all of those electrons in this wiring that are free to move around. Again, remember, the positives can't move. That's part of the atom itself, or the nucleus of the atom, and that's in the solid, it's going to be stationary. So this electron here feels a force and it starts moving around like this. And when it gets to this point, it can't jump across there, and so it just starts piling up on this side. Get a bunch of negative charge piling up there. Electrons over here, they start moving around toward the positive side of the battery. But if you lost electrons from this side, now you've got excess positive charge on that side. So I get a total charge on that. So when they talk about the total charge on a capacitor, it's not the sum of the positives and the negatives. It's the charge on one of the plates. And we always think of it as positive. So what's the charge on the positive side of the capacitor plates? That gives you that. Well, when you do that, there's a relationship between this voltage and the charge on the capacitor and the capacitance itself. And that's that the capacitance is the ratio of the charge on it to the voltage across it. There's a certain voltage difference between this negative and that positive, and the same voltage difference between this negative side and that positive side. And you end up with that equation for relationship, capacitance to charge and voltage. Now, the main thing there is, it is a relationship, it's not a functional dependence. So it's like that V equals F lambda for waves. The speed didn't depend on the frequency of the wavelength. Speed depended on properties of the medium the wave was traveling through. Frequency depended on the source. Same thing here, capacitance doesn't depend on charge and voltage. If I've got 12 volts here and I get a certain charge, say 12 coulombs of charge, if I put 9 volts here, I'm only going to get 9 coulombs of charge. Or if I put 6 volts, I'll get 6 coulombs. Or 24 volts, I'll get 24 coulombs. So it's that relationship. Capacitance depends upon physical characteristics of the capacitor itself. How is it built? And the only equation we'll have for that is then what's called a parallel plate capacitor. Capacitance of a parallel plate is going to depend on the area of the plates divided by the distance between the plates. And you've got that epsilon naught constant. So this is this one equation where we've got the epsilon naught. And you might have to use that number. And if you need that on the test, I'll give you that number. I'll put it on the board if you need that number. But then it also depends on what's in between the plates. You can have a vacuum in between them. You could have a piece of rubber in between there. You could have a piece of glass. You can have all sorts of things. Generally, what you put in between the plates is an insulating material, something that's not a good conductor of electricity. And so if we've got our parallel plates here, we've got area, we've got distance, and then we're going to fill this in with something, and that is what's called a dielectric constant. That's a material dependent number.